Hello everyone. Today I'm going to talk about gradient field and potential functions. So what's the gradient field? Gradient field is a vector field gradient pi psi. So the psi is a scalar value function, or you can say real value functions. So um, the for a given we when we generate the vector field using a real value function psi by taking gradient, then that vector field is called gradient field. So such a function, the psi is called potential function, and a gradient psi is orthogonal to the level curve for any point in the domain of psi. So which means that the gradient psi is the orthogonal to the tangential vector of level curve at any point. Then thus the gradient field point in a direction orthogonal to the level curve to of psi. So let's see this figure. So each curve represents the level curve of the potential function, and so for every single point, drawing the vector orthogonal to the tangent at each point. Okay, these the vector represent the gradient psi, which is the vector field, the gradient vector field. So here, we're gonna talk about this stuff later, but I want to just mention this first. The gradient, the cross product of gradient, the gradient psi is 0, which means that this is called which means that gradient flow or gradient field are curve free. It means that the flow is rotational, which means that if these curve, for example, these level curve represent the motion of an object, and then the gradient field, these flow, represent the way the direction where the object is moving. So as you can see that no, we don't see any the rotational flow in a gradient field. So there is no rotation of the object. So that's what that means. The flow is rotational. Okay, so this is called the curl free. Okay, so what's a curl free in math? When you take the gradient cross product of the gradient of a vector, it turns out that 0, then this is called curve free, and then the physical in physically that means there is no rotation. It's rotational. In addition, if the gradient flow gradient psi satisfy the divergence free, which means that the dot product of the gradient with a vector turns out to be 0, then gradient flow is called potential flow. So which means that this is incompressible. It doesn't diverge nor the compress. So the is if you express this box is a vector, the set of all the vector field, then the gradient field belong to the vector field definitely. And the gradient field is rotational, so which means they're curl free. And then if the gradient fields some of gradient fields satisfy divergence free, then that is called the potential field. So potential field is the set has this strongest condition. So keep in mind this we'll talk about this later. Okay, I'll circle back. But incompressible means in the irrotational, these are means that in math the divergence, the dot product of the gradient is 0, and the cross product of the gradient is 0. Okay. Now let's deep dive the meaning of the physical meaning further of the gradient field. So F equals, the gradient of psi indicate the direction in which the flow move most rapidly, because, yeah, this is true, because I mentioned already, the gradient flow is orthogonal to the tangent the point at the level core. So the gradient to give us the direction, which is uh, the most rapid move most rapidly. I mean, highest the velocity. So here's an example. Temperature in a conducting material. This is heat equations. F equals we something a constant relating to heat capacity and the gradient psi, but we assume that heat capacity is the constant is 1. So heat diffuses, this one represents the heat diffuses in the direction of the vector field, the direction in which the temperature decreases most rapidly. Yeah, makes sense. And then specifically, the temperature T T is defined by this 200 minus x squared minus y squared on that domain. So this is the domain of the temperature with the level curve. You see that the lot of circles. Okay, so these are represent the level curve, and then when you find out the gradient field by taking the gradient of the temperature, we're going to get negative 2x and the negative 2y. So for each point, we can figure out the vector field, the I mean the vector, and then as you can see that the every single the vector flow direction into toward the 0 right here, and then orthogonal to the level curve, right? And then see here's a negative sign right there, so which means that the heat flow out to the further the outer to the outer to the domain. So and then the level curve of potential function are equipotential curves, which means that the that vector field is orthogonal to the equipotential potential curve. Okay, so what's the equipotential curve? That means the that the level curve of potential functions are called the equipotential curve, and then equipotential curve is orthogonal to the gradient vector field. Okay, so here's one more last one, which might be you find challenge maybe. So you can express the vector in a polar coordinate. So let's say u r u theta is a unit vector in a polar coordinate. Then for example, let's say this is a vector u r. I mean, this is the kind of basis vector in the polar coordinate r comma theta. And then this is a basis vector in polar coordinate corresponding to theta in r comma theta. So these two vectors, we can express these two vectors in terms of the basis vector on a Cartesian coordinate system. Okay, so then we're gonna find out the orthogonal vectors of this guy onto x and y by using projection. Okay, so projecting the projection of this guy onto the basis vector I on the Cartesian coordinate system, it's gonna be this. And then if you just this guy means this one means the projection of the UR onto the vector Y, onto vector J. So then by definition, I mean, but the what by definition of projection, we can express we can say this guy is this, you are the magnitude of UR times cosine theta, and then this is the unit vector, right? Similarly, we're going to get this, right? And then for the theta, for the unit vector corresponding to theta in a polar coordinate, similarly we can say like this. Okay, so okay, that's for today.